Hello everyone, this is MOHAMMAD ASAD AMIN, lecturer in physics, Government Degree Boys College, SHAH. Today I will deliver you a lecture on a topic from chapter number 9, first year, Young Double Slit Experiment. I hope you will find this lecture interesting and informative. So first of all, to understand young double slit experiment, we should know the concept of wavefronts. A wavefront is a line or plane on which the vibrations of every point on it are in phase and are at the same distance from the source of the wave. As you see in the diagram that we are having two waves and we have taken different points on the wave. For example, P, Q, R, S, T, U, V, W. Now you see these all points are in phase and are at same distance from the source of the wave. So these all portions on the wave having same state of vibration are termed as wavefronts. Now there are three types of wavefronts: spherical wavefront, cylindrical wavefront, and plane wavefront. Spherical wavefront. If the source of light is point source, that is, if I take a light source as a point source, then the locus formed at any instant is spherical wavefront. Now we know that velocity is equals to distance upon time, and for light we take v is equals to c. So c is equals to distance, that is d, upon time t. So from this equation d is equals to ct. This is the radius of wavefront at any instant of time t. Cylindrical wavefront. If the source of light is in linear shape, then the locus formed at any instant is cylindrical wavefront, as you see in the diagram. Plane wavefront. If the source of light is in infinite distance, then any of the wave front appears a plane wavefront. For example, the light which is coming from the sun is a source of light which is at infinite distance. So all the wavefront that appears over here is called plane wavefront. Interference of light. Interference of light is defined as when two or more light waves having the same frequency, same wavelength and same amplitude meet together in a medium at a point, they cancels or enhance the effect of each other at that point. This phenomena is called interference of light waves. Types of interference. The first type of interference is called constructive interference, as you see in the first diagram, that the crest of one wave overlaps the crest of another wave, adding to a wave of increased amplitude. Now for constructive interference, the path difference is equals to m lambda where m is order equals to 0, plus minus 1, plus minus 2, plus minus 3, so on and so forth. So if you put the value of the order m in the equation, in the given equation, so for 0th order you will get 0, for first order it would be lambda, for second order 2 lambda, for third order 3 lambda, and so on and so forth. The second type of interference is called destructive interference, as you see in the second diagram. That crest of one wave overlaps the trough of another, amplitude effects are reduced. For destructive interference, part difference is equals to m plus half lambda, where m is order, which is equals to 0, plus minus 1, plus minus 2, plus minus 3, so on and so forth. So if you put the value of m in the given equation, so for 0th order the part difference is half lambda, for first order is 3 by 2 lambda, for second order is 5 by 2 lambda, so on and so forth. Young double slit experiment. The first practical demonstration of optical interference was provided by Thomas Young in 1801. His experiment gave a very strong support to the wave theory of light. Now the condition for interference is that light should be monochromatic, it should have same frequency, same wavelength, and the light sources should be phase coherent. So as you see in the diagram, that a light source is kept in front of our two slits, so the wave fronts emanate from this light source are passing through the two slits and divided into two parts, and after passing through the double slit, these wave fronts interfere with each other and a pattern is formed on the screen in the form of bright and dark bands. So this was the experiment conducted by the Youngs in support of the wave theory of light. So if you consider light as a particle, then after passing through the two slits, you will get a small impression on the screen, but the interference which is shown in the diagram is in the form of a bright and dark bands, which shows that light is an energy which spreads and interfere and forms this alternate and bright fringes on the screen. Now Young double slit experiment setup. So Young used a monochromatic light source, and when he kept that light source and illuminate in front of a single slit, the wave front after passing through the single slit will pass through the double slit A and B. Now here the distance between the two slits A and B is denoted as small d, and the distance from the slit to the screen is noted by capital L. Now when this wave front passes through A and B, now we will take this wave front as secondary wavelet. So the secondary wavelet which is reaching to point P from point A is noted as a ray R1, and the secondary wavelet which are reaching from point B to point P is denoted as a ray R2. Now since the wavelet which are going from B to P is covering more distance than those wavelets which are going from A to P, that is R2 is greater than R1. So now we can calculate the path difference by drawing a perpendicular from point A on the ray BP. So here we will get path difference BD, which is denoted as S. It means at point D the perpendicular which is drawn is showing that now AP is equals to DP, and BD, which is equals to S, is an extra distance covered by the wavelets going from B to P. So if these waves will interfere at point P in such a way that the path difference is equal to m lambda, then bright fringe will appear at point P, and if these wavelets will interfere in such a way that the path difference is half multiple of lambda or m plus half lambda, then at point P we will get a dark fringe. Now let the distance from point P to the C, which is central maxima, is small y. Experimental arrangement. The slits A and B act as two coherent sources of light. Due to interference of waves, alternate bright and dark fringes are obtained on the screen. Let the wavelength of light is equals to lambda. Distance between slits A and B is equals to small d. Distance between slit and screen is equals to L. Consider a point P on the screen where the light waves coming from slits A and B interfere such that PC is equals to y. The wave coming from A covers the distance AP equals to R1, and the waves coming from B cover the distance BP equals to R2, such that BP is greater than AP. Path difference equals to BP minus AP, which is equals to BD. So S is equals to R2 minus R1, which is equals to BD. Now consider this figure again, and in this figure we consider right angle triangle BAD. Now in this triangle sin theta is equals to perpendicular upon hypotenuse, which is BD upon AB, as perpendicular is BD and hypotenuse is AB in the triangle. So sin theta is equals to S upon D, as BD is equals to S and AB is equals to small d. Or from this equation S is equals to D sin theta, which is our equation number 1. Since the value of D is very small as compared to L, therefore theta will also be very small. In this condition we can assume that sin theta is equals to tangent theta. Now from equation 1 S is equals to D tangent theta, that is we have replaced sin theta with tangent theta, which gives an equation number 2. In right angle triangle PEC, tangent theta is equals to perpendicular upon base. Now in this triangle perpendicular is PC and base is EC, and PC is equals to y and EC is equals to L in the diagram. So tangent theta would become equal to y upon L. Putting the value of tangent theta in equation 2, we get S equals to dy upon L, or y is equals to SL upon D, which is our equation number 3. Now we will calculate fringe spacing, and for that we will consider bright fringe at P. So for bright fringe, you know the path difference is m lambda. Therefore the position of bright fringe is y is equals to m lambda L upon D. For dark fringe at P, For destructive interference, part difference between two waves is m plus half lambda. Therefore, the position of dark fringe is y equals to m plus half L lambda upon d. Now, fringe spacing is the distance between any two consecutive bright fringes or two consecutive dark fringes. So, fringe spacing or thickness of a dark fringe or a bright fringe is equal. It is denoted by delta x.